In this video, we will define electric field strength, and properties of electric field lines or electric lines of force. First of all, electric field. The charge at rest produces electric field around itself. Electric field is a region of space around a charge or a system of charges within which other charged particles experience electrostatic forces. Theoretically, electric field extends up to infinity, but practically it is limited to certain distance. Now let us define electric field strength or electric field intensity or simply electric field. To better understand the concept, look at this diagram. A charge plus Q is placed here. Now consider 2 points P and Q. A plus Q0 charge is placed at point P. It will experience a force. If the same charge is placed at point Q, the force will be different. That is, electric field strength is different at different points around the source charge plus Q. Hence, electric field strength is uniquely defined for a point. Now suppose you have to find the electric field at point P. For this, place a vanishingly small positive test charge Q0 at point P. The test charge should be vanishingly small so that it cannot alter the configuration of the system of charges. The force per unit charge is the electric field at point P due to charge plus Q. So, electric field strength at a point in an electric field is the electrostatic force per unit positive charge acting on a vanishingly small positive test charge placed at that point. Formula for electric field: E is equal to F by Q0. The test charge is considered to be vanishingly small because its presence should not alter the configuration of the charges and thus the electric field which is intended to be measured. Note: since Q0 is taken positive, the direction of electric field E is along the direction of electrostatic force F. Second point, electric force on a negatively charged particle will be opposite to the direction of electric field. Third, electric field is a vector quantity whose magnitude and direction are uniquely determined at every point in the field. Fourth, SI unit of electric field is Newton per Coulomb. Now, expression for electric field due to a point charge. To better understand, look at the diagram. Suppose you have to find the electric field strength at point P due to a charge plus Q placed at origin. For this, place a vanishingly small positive test charge Q0 at point P. The force exerted on Q0 by Q is given by F is equal to 1 by 4 pi epsilon naught Q0 by R square R cap. The direction of R cap is along the direction of R vector. This can also be written in terms of position vector. The electric field strength is E is equal to F by Q naught. Putting the value of F, the Q naught cancels and we get E is equal to 1 by 4 pi epsilon naught Q by R square unit vector R cap. This can also be written in terms of R vector. Here we see that the electric field is inversely proportional to R square. So the graph between electric field versus R square is like this. The electric field due to a point charge has a spherical symmetry. If Q is greater than 0, then the field is radially outward. Q is greater than 0 means for positive charge. If Q is less than 0, that is for negative charge, the field is radially inward. The electric field strength does not depend on the test charge Q naught. Electric field in terms of coordinates is given by E is equal to 1 by 4 pi epsilon naught Q by x square plus y square plus z square whole to the power 3 by 2 xi cap plus yj cap plus zk cap. Now, superposition principle. The electrostatic force experienced by a charge due to another charges is the vector sum of electrostatic forces due to these other charges as if they are existing individually. To better understand the concept, look at this diagram. Suppose you have to find the net force on Q1 due to Q2 minus Q3, Q4 and minus Q5 charges. For this, you have to find the individual forces like the force on Q1 due to Q2, that is F12, the force on Q1 due to Q3, F13, force on Q1 due to Q4, F14 and force on Q1 due to Q5, F15. The vector sum of all these individual forces gives the net force on Q1 due to all the charges. This simple principle is called superposition principle. The expression can also be written as this. Superposition principle holds good for electric field also. It means that net electric field E is equal to the vector sum of individual electric fields E1, E2, E3 due to individual charges. Electric field can be pictorially represented by electric lines of force, or it is also called electric field lines. Definition of electric lines of force. An electric line of force is an imaginary straight or curved path along which a unit positive charge is supposed to move when free to do so in an electric field. Electric lines of force do not physically exist, but they represent real situations. For example, first, electric lines of force due to a point charge. For Q is greater than 0, that is for positive charge, representation of electric field in terms of field vectors. The size of the arrow represents the strength of electric field. The strength of electric field is more near the charge and less away from the charge. Similarly, for Q is less than 0 or for negative charge, the strength of electric field is more near the charge and less away from the charge. Representation of electric field in terms of field lines. Electric field lines due to a positively charged. This is the electric field lines due to a negative charge. Electric field is radially outward for a positive charge. Electric field is radially inward for a negative charge. Second, electric lines of force due to a pair of equal and unlike charges. A pair of equal and unlike charges is also called electric dipole. Here, two equal and opposite charges plus q and minus q are separated by small distance. The electric field lines pattern is like this. Electric lines of force contract lengthwise to represent attraction between two unlike charges. Third, electric lines of force due to a pair of equal and like charges. Here, two like charges plus q and plus q are separated by some distance. Electric lines of force exert lateral pressure to represent repulsion between two like charges. Fourth, electric lines of force due to a uniform field. Electric field lines are parallel to each other if there is a uniform electric field. Now, properties of electric lines of force or electric field lines. First, the electric lines of force are imaginary lines. Second, a unit positive charge placed in the electric field tends to follow a path along the field line if it is free to do so. Third, the electric lines of force emanate from a positive charge and terminate on a negative charge. Fourth, the tangent to an electric field line at any point gives the direction of the electric field at that point. Fifth, the two electric lines of force can never cross each other. If they do so, then at the point of intersection there will be two tangents. It means there are two values of the electric field at that point, which is not possible. Further, electric field being a vector quantity, there can be only one resultant field at the given point, represented by one tangent at the given point for the given line of force. Sixth, electric lines of force are closer where the electric field is stronger and the lines are spread out where the electric field is weaker. Seventh, electric lines of force are perpendicular to the surface of a positively or negatively charged body. Eighth, electric lines of force contract lengthwise to represent attraction between two unlike charges. Ninth, electric lines of force exert lateral pressure to represent repulsion between two like charges. 10th, the number of lines per unit cross-sectional area perpendicular to the field lines, that is density of lines of force, is directly proportional to the magnitude of the intensity of electric field in that region. 11th, electric lines of force do not pass through a conductor. Hence, the interior of the conductor is free from the influence of the electric field. 12th, electric lines of force can pass through an insulator. Now, electric dipole. Electric dipole is a pair of equal and opposite charges separated by a very small distance. It is a system of two equal and opposite charges. The electric field produced by a dipole is known as dipole field. Electric dipole moment is a vector quantity used to measure the strength of an electric dipole. So, formula or expression for electric dipole moment is equal to Q into 2L, where 2L is the distance between two equal and opposite charges plus Q and minus Q. The magnitude of electric dipole moment is the product of magnitude of either charge and the distance between the two charges. The direction is from negative to positive charge. So it is a vector quantity whose magnitude and direction is from negative to positive charge. The SI unit of electric dipole moment is coulomb meter.